Oh, hi, everyone. I'm here to tell you a story about how I used deep learning for my image recognition project. And well, it didn't go very well. But as promised, stay until the end to hear a happy ending. So to kick off, a little bit about me first. So I currently work at GoCardless, which is a recurrent payments provider, as a data scientist. And here I create machine learning products to reduce payment failure rates and reduce payer fraud as well. But as a secondary thing, I'm also a rock climber. So this is a great passion of mine recently. And it's a real shame I can't ask you right now how many of you are aware of climbing overall, or maybe tuned in to this talk just because of climbing. But maybe you can let me know in the Q&A afterwards. And I put a picture up here of me climbing outdoors, if you haven't seen how that looks like. So this is outdoors, but actually you might be more aware of indoor climbing because that's become more popular recently. And how indoor climbing works is that you go to the climbing gym and you climb routes that are kind of set by professional route setters. And a route is just a sequence of climbing holds that is usually marked by a certain color. And you would basically try to climb up these holds to the top without falling. And once at the top, you either jump down or maybe you're using a rope if you're going much higher up, and then your partner would lower you down. And the gyms do change the routes every now and then so that, you don't need to climb the same problem over and over again. And each route would have kind of a difficulty grading. So not all problems are the same. And it goes from like really easy introductory stuff that everybody could do to some like really elite level climbing that maybe only some people in the world are able to do. So you might have heard about Adam Ondra, maybe one of the strongest climbers in the world, or Alex Honnold from the recent movie Free Solo. And if you haven't suspected yet, there's a reason why I'm talking so much about all of this climbing. And that's because the image recognition problem to which I applied deep learning and wanted to talk about is related to climbing. And that is specifically a side project that I've been working on. And it's an app called Climbicus. And what you can do with this app is basically log the climbs that you've done and even find information about them. So for example, maybe how difficult it is. So the route will have a grade, but sometimes people disagree. So maybe you can see votes on that, or votes on how good the route is, because some routes are more fun than others, or perhaps even get some tips of how to succeed at a climb if you're struggling with it. The app is not available on app stores yet. We're still actively working on it, so you won't find it there. But do let us know if you're interested and get in touch, maybe even test it out for us too. But why do this app? What's the motivation behind it? And the reason we decided to work on it is because there are apps already where you can log that I have climbed a V1 problem. So for example, in this image, I've climbed this route. But if your friend came along and climbed another V1, you wouldn't know whether it's the same V1 that you climbed or whether it's a different one, because there can be multiple problems in the gym with the same grade. So there is nothing in the system to match those two routes together. There's only some description around it, but there is no kind of unique identifier to say this is the same route, the route that you climbed is the same route as your friend did. Whereas if you could match them together, imagine all the things that you could do with that. Share information, maybe see some tips about this route. So it wouldn't be just a logbook anymore, but you could actually share information about those routes. And that's when it struck me that I could use some machine learning techniques to solve this problem and actually use image recognition techniques on a picture of a hold in order to match the two together. Because when climbers come into the gym, they look at the route, they kind of visually recognize this is the same route. So by taking a picture of it, I could train a model that could actually do this matching for me. And actually, I have played around with classification with TensorFlow before and was looking for a project to put these skills into good use and progress in that area further. And this was also a climbing related project. So another reason I was super excited about it. And it was kind of, when I thought about this idea, I kind of immediately wanted to jump on it and start developing a model. So before jumping into the model, one more trick that's worth explaining is about how do we ask users to take a picture of a route? Because as I said initially, the route is a sequence of holes going up to the top of the wall. How do you take a picture of that? Would you ask the user to try to fit the whole wall or the whole route in one picture? But you can imagine that might end up being quite inconsistent, and the image would likely contain multiple routes. So how do we know which one the user referred to? But a trick we found that works quite well here is to actually ask the user to take a picture of the starting hold. So usually when you come to climb a problem, it's actually quite obvious which ones you're going to start with. And if it's a little bit ambiguous, maybe take the biggest starting hold to make it even more obvious. So these kind of starting holds, they might repeat themselves, but they don't tend to that much. So it should work as a unique identifier for the route. And looking at some of these examples of starting holds here, so these are all different pictures, but of the same hold, we can kind of start imagining that, okay, a model perhaps can be trained on these images to say that, okay, these two holds refer to this route, these two holds refer to this route, and perhaps you would try to get multiple images of the same climate hold to give even more data to the model. So to quickly recap, because I realize there's quite a lot of information going on, what's the idea behind the app and what's the user flow? So basically, a user climbs a route and they want to log what they've done or find information about it. So with their mobile phone, using the app, they take a picture of that starting hold, and that image is then fed to the model. And the model is basically trained on all the routes available in the gym, starting holds of those routes, and is then able to predict, provided a starting hold, which route that image belongs to. So basically, provided this image would get fed into the model, and it would identify that, okay, this looks like route 1, so I will return this prediction to the user and show all of the information that we have about this route. So that's the idea. Now, how do we go about actually training this kind of model? So if you know anything about machine learning and training models, you probably know that the first step is getting the data for it. And what I did here is I basically gathered a group of friends and we all went to the gym together and took a bunch of pictures. So it was really lucky that we did this before the lockdown, before all the gyms closed. So I had the data to work with. So basically, we all went around and took pictures of the biggest starting holds, kind of doing it in a realistic manner. So I didn't tell them which, hold I took a picture of, so make it as realistic as possible. And we all did this for the evening and basically got pictures of 46 different routes in the gym. And in total, I had just over 300 images in total, so multiple images per route in order to train the model better. And I then split it into different data sets in order to kind of test the validity of my model. So I had a train set that I fed to the model, and also a validation test while I'm developing the model, and finally a test set to do a final comparison. So how do I go about training a model like that? So because I played around with TensorFlow and kind of thought that this is a good problem to use deep learning on, because I'm dealing with image data, I wanted to train a neural net, basically. And you can imagine that if you've heard about deep learning, is that usually you need a lot of data to train a neural network model. And here I just said I've got 300 images. That's not a lot, right? So, but actually a trick that you can do with deep learning is that you can use a pre-trained model, which is trained on like maybe 1 million images already, and only use your images on top of that model in order to tell the model what kind of prediction I'm expecting, or maybe fine-tune the last few layers of that model. But actually starting with a base, which is quite good and can detect color, can detect certain features. It's a little bit like starting with a child who already knows something about the world rather than starting completely from scratch. So I used a VGG 16 pre-trained convolutional base for that. I also use data augmentation, which is basically making my data set bigger artificially by taking the images that I have, but rotating them, cropping them, perhaps changing the brightness in order to make my data set more varied and help the model learn that, okay, maybe some people will climb at dusk and therefore the lighting will be different without even realistically having this data. And I also optimize some hyperparameters of the model, so kind of the standard process of training a model. And the point here is that I'm not really an expert of this. I didn't go crazy with how many things I optimized in order to come up with this model. And I was still able to get pretty good results. So to show you some examples, here I've got the first row corresponds to the kind of input image I'm giving to the model, and then what kind of route the model is giving as its first prediction and as its second prediction. So we're basically expecting the same hold or the same route to appear in the middle row. And as you can see in the first column, yep, it's providing as a first prediction the same hold, so it is understanding that this is the same route. And very interestingly, the second prediction of this brown hold, even though it is predicting the pink route, you can see that hold appears in the corner of it. So even at such a small fraction of the hold, the model will still able to say, hey, this is still a very similar class. So that was interesting. The second one refers to actually a slightly trickier problem where the first prediction is the correct one, but you can see it's a different hold. So this is where actually users disagreed about what starting hold to take a picture of when defining this route. But even with the few images that I had, the model was still able to understand, okay, these are two different holds, but they actually refer to the same route and give the right prediction. The third one is kind of straightforward, even though there is that extra hold visible in the photo, which is not ideal, but the model didn't get confused. And the last one is actually an example where it did get it wrong on the first prediction, perhaps of the color, but for the second prediction, it still got it right. So at least the second prediction is good. So perhaps we can show that to the user. So these were some examples, but I guess you're all burning to find out what is the overall performance, how well are we doing on our test set and all the images that I gathered. And basically, it's pretty good. So you can see here for all of the test sets, it's pretty high, 95% plus, except for the test set on the main accuracy. But actually, the test set was quite small, and it did have some trickier problems there too. But as you can see, if you look at top two predictions accuracy, so basically if you count something as a correct prediction, even if the second best prediction only was the correct one, you get really high accuracy metrics. So we're talking here close to 100%. So when I first saw this, I was really excited about the idea that I started here. It kind of gave me almost justification that, okay, it was worth it. Maybe this idea can really pan out, and maybe it's really worth developing this app. So happy ending, right? That was a nice short talk about a successful project in deep learning. And this is, where a lot of Kaggle competitions would end and a lot of other talks would end, because, we got good performance on the test set. What else do you need? But if you read the description of the talk, you know that my story is a little bit different. And the difference here is that I wanted to use this model in real life. I actually wanted to put it on an app and actually go to the gym and use it and see if it works to match these routes together that me and my friends are climbing. And the first problem I needed to tackle to bring it into real life is put it into production, put it in the app. And the question here was that, well, I do have a working model, but do I have a working model inside an app? And the first thing about my model that made it tricky was that it was a pretty heavy, clunky model that I was running. So it would take a long time and it would, require a lot of space. So running this model and making predictions with this model on the app that runs on a mobile device was actually off the table quite soon. It's partly because I used the pre-trained convolutional base, the big model that I talked about before, and I could have been more efficient there. But basically, And there are kind of solutions to this as well. Maybe you use TensorFlow Lite, which is specifically optimized in order to run neural net models on mobile apps. But the point here is that we kind of just wanted to test the concept at this point. We just wanted to see if people would use it. So we didn't really want it to go down this complicated path. The other option was to run the predictions on the backend server instead. Obviously, there would be a cost for the user to wait for the response a little bit longer and actually depend on Wi-Fi. But that's the kind of solution we went down for. But even that wasn't as straightforward because TensorFlow 2, had just come out. We found numerous bugs along the way and just wasn't very stable overall. So bottom line, is that none of this was a massive deal breaker. We could solve it, but that was the kind of first feeling that I got after seeing all those great accuracy metrics that, hang on, this is not the full story. It's not, even though the model is good, how do I put it on the app efficiently? But I had more problems. And the second problem I want to talk about is dealing with unexpected images. Because one thing that might happen when you actually use the app in the gym is that people might take a picture by accident. So maybe they didn't place it on the starting hole. Maybe they took a picture of the general area overall. Or perhaps they're just playing out with the app at home and, pointing it to somebody's face or my face eating, for example, or what else people can think of trying to use the app for. I don't even want to imagine. So basically, in these cases, I don't want the model to say, oh, this is route 1 or route 2. I actually wanted to, say this is an invalid picture. So I wanted to give a prediction to a class which is kind of unknown or invalid rather than, its best possible guess what route it might be if it's no route at all. And when I started looking into this, I was actually surprised to find it's not a very straightforward problem to solve with a classification model. And even really good models can struggle with that. So an example I want to talk about here is that even state-of-the-art models, that trained on millions of images that can train 1,000 categories really well, might have a problem with that. And an example of this could be where a model is trained to predict a toilet seat amongst the 1,000 categories with really high accuracy to say that, okay, this is toilet seat or not. But if it's provided a plate, so an image of a completely different class, it doesn't have an option to say, I don't know. It will try to give its best prediction. So, and plates and toilet seats can look quite similar sometimes. So it's quite likely to give that prediction. So it doesn't have, that unknown understanding, even though to us, it's ridiculous that it would make such a prediction. Now, how can it be a good model if it's doing something like that? Now, not to say there are no solutions to this. I think there's even a talk at this PyData Global talking about this problem and solutions to it. But again, none were that straightforward. None were like that I can implement something quickly and bring my model to the gym and try it out. So it was kind of another sign for me that just getting high accuracy isn't enough to be successful using this app at the gym. But actually, the third problem was kind of a real nail in the coffin. And that's when the routes get reset. If you remember, I said at the beginning that happens. So that means I need to retrain my model with the new classes and kind of remove old classes as well. And I kind of realized that I will need to retrain my model right from the start. But I thought, routes get reset in chunks every few weeks. When I will see that users are uploading, new routes, I can retrain the model then. Perhaps even automate it. And do it more regularly. But that was actually before I tried setting up GPU instances on the cloud and considering that the costs. And even training one model was already quite a lot. And I was thinking, what will happen with the cost once I do it regularly? And dream big. If the app really kicks off, imagine doing that for multiple gyms and, some areas getting reset every now and then. That would need basically continuously training models and, not even thinking about the synchronization of all of that. Just the cost is quite large. And this was kind of the point, and I was already thinking about how to set up this infrastructure. But just before committing to this cost and this approach, I was a little bit wait a second, am I missing something here? Because this just seemed quite complicated, overly complicated. And I knew that there are examples out there, that deal with many more classes than the 46 I was dealing here. And once I kind of stopped thinking about the technique that I was trying to apply here, and instead of this problem that I now had a much better understanding of, that I've got these images and these are all the problems that I might have with the app, once I started thinking about how do I solve my problem in particular, well, it didn't take me very long to find out that there's a better approach to this. And that approach is content-based image retrieval. And the phrasing here of my problem in this context would be that given a picture of a hold, what I need to do is find the most similar image in the database. Not really allocate it to an abstract class that is defined by abstract features that are learned by algorithm, but just literally finding the most similar looking thing in the images that I have in the database. And again, thinking about my problem specifically, I am expecting users to upload images of the exact same thing, the exact same hold, because these are the specific instructions I'm giving to the user. Please take a picture of the biggest starting hold. So it should be the same object. Not really an abstract cat or a dog that I could train my model to recognize, but that might look different every time. This is here literally the exact unique and fixed object. And yes, they can be from a slightly different angle or at a different lighting or a scale if people move, but it's still the same object. And I was surprised to find, and definitely just a surprise for me, not somebody more experienced, is that there are good solutions to this exact same problem already that does not include deep learning. And actually within open source libraries like Open Computer Vision that have been around for a while with pretty simple algorithms, that have been developed since the 70s to deal with that. So I specifically here used ORB algorithm, brute force matcher from Open Computer Vision. But the idea behind these algorithms is the following. So the first step is that for a given image, you try to find features in it. So kind of distinctive things that define what's in it. And it's kind of features and corners edges and corners that tend to work well. And the second thing you need to do is describe them numerically so that you can do calculations with it afterwards. And these descriptors of those features are engineered to be robust to that change in lighting, scale, or orientation. So that's kind of the grunt work in these algorithms that deal with it well. And then the third step is to use these descriptors that you now hold in your database in order to retrieve the most similar image to a provided image. So for example, here, if a user provided this white root image, the white red spot root, what you do is you take all the features in that image and compare it to all the features found in another image and use a distance-based calculation to try and figure out, okay, how similar are these features? And then at the end, when you compared all these different features, you get a total distance between the two images. So here we have 238 with a different one. It's also quite high, but with a different picture, but of the same root, it's much shorter. So this is actually the image that would be retrieved. And so talking about specific examples here and how it deals, one point is that another point I wanted to make is that these calculations are super fast, unlike like a 20 layer neural net model. And it deals well with the scale here. You can see it's further away, but it still works quite well. Lighting is different, still captures the features. And with the other one where the angle is slightly different, it still works quite well. And the overall performance is actually 99%. So it pretty much matches the neural net performance here. Out of the 300 images that I had, only 4 were returned that actually the closest image return wasn't of the correct root. So it matches it. But actually what I want to argue is that it does better than that. It not only matches it, but it exceeds it. And that's because all the other problems that I had before, and it wasn't really straightforward to deal with neural nets, it's actually much easier now with CBIR. And The first one that it deals nicely with is filtering out unexpected images. And that's because of that distance that I talked about between images. So now when I use this technique and compare it with something completely different, and it turns out me eating a ceviche is quite different from a climbing hold, it's immediately obvious that this is an invalid picture. So I can rule that out and ask the user to upload a different picture. The second problem it deals nicely with is dealing with new classes. It's the same algorithm. I don't need to retrain anything. All I need to do is add a picture of that new hold into the database. And from that point onwards, any new picture will be compared against it with the exact same algorithm. And it still works quite well. So no expensive GPU instances to continuously retrain models needed. You get it for free. And the final thing that it also solves is it's much easier to deploy. So basically, open computer vision has been around for a while. It's stable and reliable. And as I said before, the calculations are light and fast, straightforward to run on the app. And all of this translates in that is quite cheaper as well. So no GPU instances needed to retrain the models, etc. So another happy ending, right? But again, no technique is perfect and there are always problems to solve. So here, for example, CBIR perhaps might not abstractly understand what a hold is and match on the wrong features. So here you can see it still gives the right prediction, but actually it's matching on the informational plate rather than the hold itself. So if there would appear another hold with the exact same plate, then it might give the wrong prediction. Or perhaps remember that trick example that the neural net did well with, where the users disagreed which was the starting hold. CBIR, because it looks for specific objects in it, it will think it's a different route. So again, might struggle with that. Or black holes might get whiter as they get chalkier. So chalk is something climbers use to kind of soak up moisture. So a lot of black holes tend to start looking white. So again, the model might struggle. So it's not perfect and there are problems to solve. But the point I want to make here, and that's the kind of key learning if you take away anything from this, is that this approach should have been my baseline. This approach should have been what I start with, because it's much simpler, it gives pretty good performance, and it's just perfect for testing that concept. It's something quick that you can use and reliable to deploy. Whereas I kind of jumped in for the excitement of the technique, thinking at that point it was a learning project, so it didn't really matter what I use or how I define my problem. But very soon I realized actually I kind of want to solve the problem and I want to build this app, so actually other things become more important. And the other sad thing about it is that this is not news. There's been lots of talks about this, and in PyData even. So check out these links. They talk about this as well in a very engaging way. And I miss them. But I do feel more calm now because I know that you guys haven't missed mine and hope you'll do better than me. Thanks for listening.